In today's tutorial about the chemistry of medicinal drugs, thyroxine is our subject. It is a thyroid hormone for the treatment of problems with the thyroid gland. Well, we notice it is obviously an amino acid. And here we have overall 4 iodine atoms within this molecule. For the synthesis, one can preferentially start with tyrosine. It's also an amino acid, but with no iodines. So indeed, those iodines here at that part could be introduced just by an oxidative process. Well, let's compare it with this one. Here is also a phenol, and in the last step of the synthesis with sodium iodide and sodium hypochlorite, with an electrophilic aromatic substitution, those 2 iodines are introduced. We could do also here in this case introducing those iodines here, but actually in this case it's not introduced directly by an iodination, but indirectly via a nitration. Here are those 2 nitrogens. Then the hydrogenation, reducing, and finally with sodium nitrite forming diazonium salts, and in a Sandmeyer type reaction we introduce the iodides there. So what we want to figure out now is, by going through this synthetic procedure, why aren't all four iodides introduced by the same process, by the very facile electrophilic aromatic substitution? There must be a reason, and we will see what is the reason. So, starting with tyrosine, first step, typical reaction conditions for the nitration. It is nitrated twice in those 2 free ortho positions of the phenol. Then we are in need for introducing protective groups. With acetic acid anhydride, we achieve an acetylation of the amino group. With thionyl chloride, we will then form the acid chloride, and by treatment with ethanol, we will get to the carboxylic acid ethyl ester. Here is this intermediary product. So, why do we need that protection? Well, because the next step is the tosylation in pyridine. Without the acetyl protecting group, the amino group would be tosylated. But we want to achieve the tosylation of this phenol. So with pyridine, it is of course deprotonated. Then we have the nucleophilic oxide, which is tosylated. That means the OH group is transformed into a good leaving group, a tosylate. And now it is clear why we need those 2 nitro groups to activate nucleophilic aromatic substitution. Because this group is introduced by nucleophilic aromatic substitution. We have as an intermediate the tosylate here. It is the leaving group, and this oxygen is the nucleophile, will attack the aromatic system addition elimination process, and by this carbon oxygen bond is formed. Now with hydrogen on palladium, the two nitro groups are reduced to anilines. Then sodium nitrate under acidic conditions will give two diazonium salts. Treatment with iodide will introduce those two iodine atoms. Then the combination of acetic acid and the very strong acid hydrogen iodide will deprotect both the ester and that amide, and moreover will also hydrolyze this ether bond. The CH3 group is eliminated to the phenol, and now the phenol is active enough for an electrophilic aromatic substitution with sodium iodide, sodium hypochlorite. By oxidation, the electrophilic iodine is formed. Well, and all those processes will succeed in remarkable good yields above 85 or even above 90%. A very nice synthesis of this rather complex target molecule. Thanks for listening.